Hi, everyone. Welcome to your first lecture. So for right now, we're going over the very first chapter in your textbook, Chapter 1, the process of science. So beginning with every lecture, I will have learning objectives, and these are kind of a good way for you to really make sure that you're understanding exactly what you need to from each of the lectures. So make sure that you kind of go over this maybe before and after lecture and make sure that you took away some of these key points. There's obviously a lot more to the lectures and probably more in the textbook as well. For the most part, what you're getting from the lectures is mostly what you'll be tested on. The book does have some things that will help kind of clarify or maybe some extra things you might see here and there, but for the most part, you should be getting most things from the lecture. Okay. So our first learning objective for chapter 1 is that you are going to be able to explain that science is a process in which scientists conduct carefully designed studies to answer questions or test hypotheses. Our second learning objective is you will be able to understand that the media's report on scientific information is not always completely accurate in how they portray the conclusions of scientific studies. You will be able to identify scientific theories from everyday theories. And lastly, you will learn how to interpret and analyze experiments. All right, so getting into it, chapter 1 is about a Java report. So basically, it focuses pretty heavily on caffeine and its effects on humans, whether they're good or bad. So depending on how you like to do this, it might change throughout the semester. I usually recommend that you would read the book beforehand and then listen to the lecture, or you might want to do a little bit of half and half. However it is that you want to do it, the important thing is you really do want to both listen to the lecture and read the book to sort of reinforce everything that you're hearing from me. And hopefully the idea is that anything you've read in the book will be cleared up by me. And if it's not, please feel free to send me a question, ask your fellow classmates, come to office hours, whatever it might be. Okay, so when we're getting into chapter 1, the big focus is on setting up what science is, the scientific method, all of that good stuff. And hopefully this is all stuff you've learned in the past. You might have forgotten it, or you might have learned different variations of it because everyone can teach it a little bit different. But we're going to go over some of the basics right now that are going to set you up for the rest of this course. So science is a method to answer questions. It's a process of using different observations and experiments to draw evidence-based conclusions. So this is one of the most important parts of science. It's evidence-based. We don't use anecdotal facts. We don't use stories. Anecdotal stuff is stuff that's your own personal experience or stuff that you might have heard secondhand, but we use actual evidence, right? So it's something that had to have happened in an experiment or something you see with your eye through an actual observation. All of science is using evidence-based conclusions. So science is basically just a way of knowing. It's a way of figuring stuff out, right? We have questions about everything in life, usually. And the way that we figure it out is by testing it or researching it, whatever it might be. And even if we're researching it, say, on Google, odds are we can find the answer to a lot of different things, and it's because someone else has taken it upon them to experiment and actually figure out the answer to the question. When we are Googling different things, we need to be really careful. And especially now in our current climate, I'm sure you all know that the media can be difficult to trust, no matter what it is, right? Science, politics, anything, right? With what we're going through right now in media, you never know what's right and you never know what's wrong. And it's really, really difficult to do your research. So you kind of want to make sure you're reading into all of these sort of scientific claims as well. So you can see things like, I'm sure you guys have seen things similar to this, like lemons contain 22 anti-cancer compounds and reduce risk of cancer by 50%. Could that be true? Maybe. Might that be a little bit of an exaggeration? Also maybe, right? So you have to kind of dig a little bit deeper. And a lot of times the media actually focuses on an important scientific study, and it might have been one that's peer reviewed and is actually really sought after, but they might actually kind of condense the information down and take out a lot of really key facts or possibly change the narrative a little bit. So be careful. There is a lot of information on the web, especially through social media, and social media tends to twist things pretty often. Again, in every sort of direction. So it's not something that you can trust from any side of any sort of media or social media. So how do scientists draw conclusions? Well, like we said earlier, they're doing it based on evidence. And you'll see lots of different things in the news or on social media, possibly. I'm sure you guys have all seen this guy right here. This is the infamous Dr. Oz. Um, I am not a huge fan of Dr. Oz, and there's a lot of different reasons why. But these are the kind of people you kind of want to watch out for, right? Sometimes they have an actual title, sometimes they don't, sometimes they sort of make up their own title. But they kind of push things that sound a little bit too good to be true, like miracle diet pills. There's no such thing, right? We know a lot of different things go into your diet, a lot of different things go into how active or fit you are. It's not just something that can be fixed by one pill. People that are pushing this kind of thing are using really like flowery language. Again, that kind of sounds too good to be true. And, people who do this, like Dr. Oz, they see themselves as kind of a cheerleader for some sort of either it's a product or a movement, whatever it is, but they stand by it really heavily, and usually it's motivated a lot by money. It could be motivated by other things as well. But these are the kind of things you want to watch out for, and not just with individuals, but anything you see in the media. And this is honestly one of my biggest goals for you in this course is to be able to look at things that you see in the media, whether it's on the news or in social media, or if you're talking with your cousin or your friend, whatever it is. I want you to be able to look at different things that you see in the media and be able to take away what might be legitimate and what might not be so legitimate. And it does require research and it requires some critical thinking. And that's really a big takeaway from this class is not to believe everything you read. And again, it doesn't matter which side it is. It might even be on a scientific side, but it doesn't mean that it's always fact, right? So science is a way of knowing. We basically tell you as much as we know with science, and that changes every minute of every day. So what you know now based on science might change tomorrow when some different scientific experiment comes out or we've sort of done something that contradicts it. Okay. So look out for people or products like this that use really flowery language, like things that sound kind of too good to be true. And again, you'll see different things in the news about coffee, right? And this is what your book focuses on. So you'll see coffee causes cancers, but it also prevents cancer. It prevents other diseases. Caffeine's poisonous. Caffeine's really good for you. You see so many different ways that caffeine or coffee can affect you. And here we have all of the benefits, right? So we have benefits, we have disadvantages. What do we actually believe? Right? And that's why we actually go through, we do an experiment, and we figure out how we can draw conclusions based on the evidence that we have. Okay. So again, whenever scientists draw conclusions, they're using their best evidence available. Again, this changes often. Science never stops. There's always people doing scientific experiments. There's people getting grants. There's people doing experiments for different things. That's why in the case of coronavirus, right, we're all going through this right now. Our information is changing daily, and it's really frustrating, right? But of course it's changing daily because the evidence that we have is changing daily. So we can only say what we know based on the evidence that we have. And that changes very, very frequently. So when you're reading different media stories like this, again, often they're linked to a article like this one. This is what we call a peer-reviewed article. Let's see here if I can write clearly. Okay, and peer-reviewed is exactly what it sounds like. It means that it's been reviewed by peers, and not just any peers. So this one is entitled The Impact of Coffee and its Selected Bioactive Compounds on the Development and Progression of Colorectal Cancer in Vivo and in Vitro. So when they went to submit this to a scientific journal, it actually had to go through different rounds of basically scientific experts who had to approve this paper and ask different questions. It probably had to go through different rounds of the authors actually changing things or possibly performing other experiments. So this is pretty extensive, this peer review process, and you guys are actually going to be analyzing a scientific paper in lab because again, even though science is probably not what you're going to be getting into, it's something that you want to know how to read, and science is very dry and boring sometimes. So being able to pull out the facts and understand what's real and what's not real is super important, and to have that critical thinking is something that you really need to be able to take with you. Okay, so we normally look for peer review as something that tells us that the science was performed properly. That doesn't mean that all peer-reviewed articles were performed properly. Okay, and that's something that you have to take into account. Sometimes different peer-reviewed articles come out against other peer-reviewed articles that have been in the past. It depends on the evidence. Usually they're not doing it maliciously, it's just something that happens when you're doing science. Okay. So again, the conclusion might be modified in the future. It's a never-ending process. So don't get frustrated with the idea that science changes. That's good. Science should change. People should be getting smarter. We should be continually evolving. So science isn't going to be the same in this class as it will be when, say, your children take this class. It's probably not even the same as when you took a similar class in high school, even if you just got out of high school. Okay, so this is really important. Now we're going to go over the scientific method. I'm sure you've all had some semblance of this, but this is something you definitely want to understand. You will have a class activity and a lab on it, and you will probably see different variations of this on the exam. And not so much like I'm going to ask you to list what these are, but you're going to have to actually practically use them. So make sure that you understand them. When first starting with the scientific method, the very first thing that we do is we make an observation. And you've been doing this since you were a little kid, right? You look over, you ask your parents, why, what, where, how. You ask so many different questions. And you didn't just do that when you're a little kid, you still do that. Maybe not as much, but hopefully as much, if not more, you're still asking questions. And when you start doing that, you're doing it based off an observation, so off of seeing something. So let's say I'm at the park and I see these birds and I see that I've got really big birds and really small birds. So that's my observation, right? I see, okay, I've got really big birds and really small birds. Then I start to think about that observation and I start to formulate questions, right? So now we're getting to the question stage. And now I'm wondering, okay, why do I have small birds and why do I have big birds? So I might start to do some previous research. We've got a wonderful thing called the internet now, and it knows quite a bit, not everything, but quite a bit. So I start to look up, let's say I'm looking at mynah birds, arguably one of our worst birds here. But I'm looking at mynah birds because what else do I do during this time? So I'm looking at mynah birds and I start researching why are some mynah birds really large and why are some really small, right? And I do some research. I kind of figure out, okay, like, and I don't know if this is true, I doubt it, but let's say that males tend to be much larger than females, okay? So I look at that and I then want to make a hypothesis. A hypothesis is what you've always heard, an educated guess, right? So now I'm going to make a hypothesis as to why I think I might be seeing these bigger and smaller birds. And let's say I know that the bigger birds are males, or I think that they're males. Why might males be bigger than females, right? So I've got to come up with some sort of question. Let's say that I'm thinking males are bigger than females because they're going out to get more food, they're expending more energy, so they therefore have to eat more food to keep up with that caloric intake, right? This is pretty rough example, but now I've made my hypothesis. So once I make my hypothesis, it usually also comes with predictions. Sorry, let's see if I can write. Pretty ugly writing, but that's okay. So once I have my hypothesis and predictions, then I can start my experiment. And my experiment is specifically testing, oops, my predictions. Okay, it is also testing my hypothesis, but more so my predictions. And we'll get into how you formulate a hypothesis and predictions in just a second. So we go through an experiment, we get our results, we get our data, and then we have to analyze them, right? So we analyze our data using different things, doing different statistics on it, whatever it might be, making up some graphs, making up some tables, and then, and only then, can I draw conclusions based on the evidence that I got from my results that ultimately came from my experiment. So thinking about this scientific method, what do you think the difference between an observation and a hypothesis is? Normally I would have you guys weigh in a little bit, but just to jump right to it, an observation, right, is something that you're seeing with your eyes. So it's something that's very clear, night and day, possibly. I mean, it might not be that clear. That's why you have questions about it. But say my observation about the birds. I can see that there's big birds and I can see that there's small birds, right? And then my hypothesis is that male birds are larger because I think that they expend more calories, right? So that part I don't know. I might have seen a little bit about it in my research, but for the most part, it's just a guess that I've come up with to support what I saw in my observation. So they are different and they're not part of the same step either. So an observation is what you're seeing with your eyes, and a hypothesis is basically your educated guess as to why you're seeing that. Okay. When you're forming a scientific hypothesis, a few things to keep in mind. One, a hypothesis is never, never, ever, ever proven. Okay. So please never say that. It is something I never want to hear. A hypothesis can be accepted or supported, but it is never proven. Okay. If it's false, we can say that we reject it, or we can say we do not support it. Right? And once it's false, we basically can throw it out of the consideration as a possible answer. It's not a possible answer. We've basically, in some sense, rejected it, right? We didn't necessarily prove it wrong. You could kind of say proven wrong. You wouldn't say it to anyone else, but you could kind of say it in your own little head, right? But you cannot say that a hypothesis is ever proven because we really can never prove any sort of hypothesis or scientific theory. So again, if the data supports the hypothesis, we can accept it or we can support it until further testing and data show otherwise. This is why science is continually evolving. We might support it today, but then tomorrow we come up with something that rejects it. And that's okay. That's how science is supposed to be. It's a process. So when we're talking about a hypothesis and prediction, I'll talk about them a little bit more in the lab as well. But hypotheses and predictions are a little bit different. I'll go into a little bit more in the lab about how we formulate them as an if-then statement. I don't particularly love if-then statements, but that's kind of how you were taught, and I'm going to put a little bit of a twist on it for you. But once we have that hypothesis and prediction, we might have more than one, and that's okay, but we have at least one of each. Then we can actually come up with our experiment. So we've got to actually really think through what our experiment is, what we're testing, how we're going to test it, how we're going to analyze it before we go through the actual process. So in this example here, we're looking at a control group and an experimental group. So we've got two different groups, and we've got a few different things that we're doing. So our control group is going to be receiving what's called a placebo, which we'll talk about in just a second. Our experimental group is receiving a test treatment. So they're both receiving the same amount of liquid before the test, so they don't know whether they're receiving a placebo or a test. And then we're going to be giving them a memory test. So we're going to be giving it to them at the exact same times for both groups. We're going to give them one in the morning and one in the afternoon, and then we're just going to be doing it on different days. And the way that we're going to analyze this data is from their memory test scores, right? So are their memory test scores better or worse? And you can see the results already here. So for our control group, the afternoon scores were worse than our morning scores. For our experimental group, who had the caffeine, right? They had the coffee. Their afternoon scores were the same as their morning scores. So our overall conclusion from this is that caffeinated coffee prevents memory decline in this population. Okay, and that's important because we can't say that caffeinated coffee provides or prevents memory decline, period. We don't know if that's completely true, right? We might not have a very diverse group here. We might have a pretty diverse group, but we really can only apply it to this specific population of people. So when we're setting up an experiment, we have different variables that we're considering, okay? And a variable is basically just an item or a factor that we can change or that gets changed. So when we're looking at our control group and our experimental group, both of these are variables, and then there's different variables within these groups as well. The experimental group is what's experiencing the independent variable. Okay, so the independent variable is the one that we deliberately change. So remember our experimental group, they're the guys that received the coffee. So here we're changing the amount of caffeine that they're using versus our placebo treatment. This is our control group, okay? So I'll write control up here too. We always have a control in an experiment because you always want to have essentially what is a baseline to compare your experimental group to, okay? So I have experimental and control, and our experimental is our test treatment. That's what our independent variable is, okay? So our independent variable here, I'll write IV, is caffeine, right? So amount of caffeine. So in this case, we have 0 versus, I don't know how much caffeine is in this, but let's just say 12 ounces of coffee. Okay, so that's our independent variable. Now, we also have a dependent variable, which I'll talk about in just a second. But with our control group, they're the ones that are receiving a placebo. And you guys have probably all heard of placebo effect. Placebo is basically just means it's a fake treatment that mimics the experience of the experimental groups, because you don't want someone knowing that they have the placebo, because then they might change their behavior, right? So you can't tell the group, hey, you also wouldn't want them, you usually want a pretty blind experimental group. You probably wouldn't want to tell them they're receiving caffeine because they might also change their behavior, but you definitely don't want to tell the placebo that they have a placebo, because then they can change it depending on how they're going. So you see this a lot with like sugar pills and stuff. That's what a placebo is, and that's why we essentially never inform them that they have the placebo, is we don't want them changing the results of our experiment. Okay. Oops. I can't go back, but we didn't talk about dependent variable. But dependent variable basically is what's being changed by the independent variable. So our independent variable is usually down here if we're graphing it, right? So let's say we have 0 and then we have, let's just call it 12 for caffeine. So our independent variable down here is caffeine. That's bad. Okay, and then usually our dependent variable goes up here, and these would be our memory test scores, right? So let's say they go from 0 to 100, and let's say that our guys with 0, and remember we actually had 2 different groups within these. So we had one that was, let's see, basically we'll have 2 bars. So we had one that was tested in the morning, right? So let's say this was their morning one, and then this was their afternoon score. Okay, and so actually their afternoon was worse, right? So let's say this was their morning, and then this was their afternoon. And then for over here, our caffeinated guys, this was their morning, and this was their afternoon. So they were both the same. I know it's a terrible graph and probably hard to see, but basically our dependent variable is over here, and it's the one that's being changed as a result of our independent variable. Okay. So that's our experiment. That's kind of a little bit of how we're setting up our experiment, and you'll get more practice with that as we go, especially in lab. But now we're kind of moving on to what a scientific theory is at its very, very core, because we hear theory quite a bit. And basically, a theory is just referring to some sort of idea, right? In science, when we refer to a theory, it's actually a hypothesis that has never been disproved. So again, hypotheses don't get proven, so we've never proved a scientific theory, but we've also never not proven it, right? So it's never been disproved, even after lots and lots of really rigorous testing. So these kind of theories are things that have been done by thousands and thousands of scientific experiments. So here's a question on your lab, if you guys are listening well. If we were to do an experiment in class, and we form a theory or we have a hypothesis from that, could that hypothesis be considered a scientific theory based on our one experiment in lab? The answer is no, right? We can't just call something a theory just because we didn't disprove it. It has to agree with lots and lots of other research that's been tested in many, many different ways, really rigorously. So we wouldn't be ever doing that in class, although what we do in class might line up pretty well with scientific theories. So that could be it, but something that we're doing as like a novel experiment, let's say in class, we could not call a scientific theory. So to compare a little bit, like an everyday theory could just be something that's based on your own personal experience and knowledge. And this is something like, I know if I carry my umbrella today, it's not going to rain. but if I leave it in the car, I'm going to get drenched, right? So that's kind of whatever everyday theory is. And usually it's pretty opinion based or anecdotal, and usually it's your own personal opinion, though it could be formed off the experiences of others. But again, a scientific theory is supported by thousands of experiments, and it's something like gravity, right? Or evolution by natural selection, or cell theory, which we'll get into in our unit 2 of the class. So these are scientific theories. They've never been disproven. So through the process of science, we are usually also finding patterns, right? So as an example, in the 1990s, there were a few studies done on Gila River Pima Indians, and they found that over 50% of the population had adult onset diabetes, which was considered one of the highest rates in the world. So why did they have one of the highest rates of adult onset diabetes, right? And that's something that, there's lots of conjecture, there's lots of different hypotheses for it, but they haven't still quite figured it. And there's lots of different factors that can go into this too. Remember this, is that just because you support one hypothesis doesn't mean that another hypothesis can't also be supported. So it might be that it's genetic, right? It might also be diet. Let's say they're eating a lot of fried foods or a lot of really sugary foods, things that are contributing to diabetes. So there's lots of different things that could be going into this, and a study might only test just one of them. But we're looking for patterns, right? So we observe this pattern, and then we can show a pretty consistent relationship or link between different variables. This is what we call a correlation, right? Whenever we've got a consistent relationship or link between these variables, it's a correlation. I know most of you have probably heard this. Correlation does not equal causation, okay? So just because something's correlated doesn't prove that one variable causes the other. A lot of times they are linked, and a lot of times there is a reason that they run together, but it doesn't prove that one causes the other. So here's an example. So it's a study done in 2000 at a VA medical center here in Hawaii. And you can see we've got incidence percent over here on the left. We've got coffee intake over here. And you can see that we've got different amounts of coffee drinkers basically up here, right? So how much they drink per day. And we see that less coffee actually correlates with higher incidence of Parkinson's disease in these 8,000 Japanese American men that they tested. They followed them for over 30 years, so this is pretty intense data that they're collecting. But they also saw that more coffee correlates with lower incidence of Parkinson's disease. So looking at this study, if you're thinking that the correlation is the causation, you would say coffee lowers your incidence of Parkinson's disease, in this population especially. But does it necessarily? There might be other things at play, right? So just because there's a correlation between these two variables doesn't mean that one causes the other. Here's another example of a temperature anomaly versus CO2 concentration. So this is kind of when we'll get into climate change here in a few lectures. But again, not necessarily the same as causation. So you can see our temperature is going up over time, and so is our CO2 concentration. Temperature is varying a little bit more, right? So it's kind of up and down here, whereas CO2 concentration has a pretty steady increase the entire time. Is our temperature increasing because of increased CO2? Maybe, right? We'll get into that a little bit more later, but it's probably not the only reason. Same thing with, is CO2 increasing because of our temperature increasing? Maybe, right? But again, probably not the only reason. There's probably multiple factors at play, or it's possible that they're completely unrelated, even though they have a pretty high correlation. Basically any correlation that's close to 100 or 1, right? Which 69% is pretty high correlation. That's when you have a really, really good chance that those variables are linked together in some way. Again, not the cause, a really good linkage. So you're looking here at US postal charges versus increases in CO2. So you can see as postal charges are increasing, so is global temperature as well as CO2. Does that mean that the US postal charges are driving global warming? Probably not. Could they be contributing? Maybe, but they're probably not causing one or the other. This is my favorite. So we have a number of people who drowned by falling into a pool with films Nicolas Cage appeared in, and you can see that they correlate really, really well together. They have their highs and lows pretty much together. Does Nicolas Cage cause people to drown? I like to think not. You never know. But it's probably not the reason why we've had so many people drowning in pools, right? At certain times where Nick Cage happens to be in many movies. So this is probably something that we're seeing as a coincidence, or they could somehow be correlated, but again, not causing the other one. This one is probably very, very random. And this is one reason why we always say be wary of statistics too, right? You can always lie with statistics, even if you go through the proper measures. There's always a crazy statistic you can find that can kind of help support your cause in one way or another. So you've always kind of got to be a little bit careful of that. Okay, so for your class activity that you guys will have due, you are basically going to go through the anatomy of an experiment, and it's very similar to the coffee example that we did here. So go through it, do your best that you can. You do have a part where you will need to graph, and you're only graphing the first 5. I think there's 10 total. So only graph the first 5. You can either do it by printing it and you can hand draw it however you want. Make sure that you label the axes, or you can do it right over it on a PDF or in a Word document. Probably the easiest way is just to insert a graph and then do it like that on your computer. If you have any questions, please let me know. You're welcome to do it in groups or with a partner. Just be sure to link up in some way that's safe for you to do so. Obviously, virtually would be your best bet. Okay, and that's the end of chapter 1. Please let me know if you have any further questions.